Hi, everybody. We're going to start an exploration of kinematics by looking at linear motion. And specifically, we're going to be looking at the ideas of distance versus displacement and velocity versus speed. And so we're going to start off just by looking at this concept called distance and displacement. It starts with something we call position. And position is basically just saying, here I am. Oftentimes you have to describe position by putting on a coordinate system and coming up with like an XY point that puts you on a Cartesian plane. So in physics, we often use different variables to talk about this position, but it's often called d. So we'll see that meaning like distance or displacement. In AP physics, we often give it the letter s. Sorry, we give it the letter x. Sorry. We also give it the letter y sometimes when we're talking about vertical position. And there's a traditional thing in AP physics where they give the letter s. And so these are all just different ways that you could talk about position. So be wary of all of those things. When we talk about distance, what we're talking about is a scalar quantity that is just referring to the total amount of distance that you've gone without respect to your direction. And so I have a picture of just like a fly flying towards this hamburger over here. And the distance that the fly would travel as it went through this circuitous path to get to the hamburger would actually be a lot bigger than the displacement of 6 meters, which is the average distance from point A to point B. So the fly would actually travel further because of its circuitous route. The idea of displacement, though, is actually the shortest possible distance between 2 points. Now imagine if the fly does this circuitous route and say it actually flew like 9 meters or something, it would still move a displacement from point A to point B of 6 meters to the right. So displacement is actually a vector quantity, and you have to actually say the direction associated with it. So when you say distances, you just report like 6 meters. But when you say displacements, you'll say something like 6 meters to the right. And oftentimes in physics, we're going to call that the positive direction to the right. So you might say plus 6 meters. Or you might say that the displacement from the burger to the fly is negative 6 meters to the left. Okay. So next one has a little question to think about that. So notice like this baby here is crawling towards the right, and then it turns left and it goes up. Now, if you ask what is the distance that the baby crawled, well, if it went 6 feet and then 3 feet, it's just 9 feet. Okay, but if you want to know the displacement of the baby, that's really what it's saying is what is the shortest distance from the beginning to the end of the path. Then you'd have to use some Pythagorean theorem right there to figure out that the displacement is actually about 6.7 feet from here to here using the hypotenuse of your right triangle, and the direction that it travels is somewhat to the left of its original path. Now you could go ahead and use inverse tangent function right there to figure out that actual angle, but you don't need to. It's okay. Next word we have is speed. So speed actually comes from the basic formula. Speed is equal to distance over time. Now notice the distance part of this. Okay, that is going to be going into what we mean by speed. Speed is a scalar quantity, and we don't concern ourselves with direction when we're talking about speed. That's because we're using the scalar of distance. Now, if you think about your car's speedometer right here, that's actually reading your speed and not what we're going to call your velocity, because it doesn't really matter if I'm going north, east, south, or west. If I'm going 60, I'm just going 60 miles per hour. Okay, so that's what speed is. And we want to differentiate sometimes between instantaneous speed, which is your speed at any given moment. Okay, so that could be changing if you're accelerating and slowing down and stuff like that, compared to your average speed, which is just your total distance divided by your total time. The twin concept with speed is velocity. And velocity is actually a vector quantity because velocity does concern itself with direction. So when we're talking about velocity, we're saying that you're going a certain speed in a certain direction. And when you put both of those together, now we're talking about velocity. And if you notice the average velocity equation here shows it as being displacement over change of time, then you have to actually figure out your actual displacement before you can figure out the velocity when we're talking about your average velocity. Notice the formulas that we have associated with that, but really average velocity, that's what this little bar over the top means, is equal to a change of position over time. And oftentimes we'll define change of position by being a final position minus an initial position. Okay, and that is oftentimes what we just call velocity. Now, going back to our baby problem, we already calculated out that the baby had gone a distance of 9 feet, and it had gone a velocity of 6.7 feet, slightly to the left of its original path. And so if you want to know what the speed the baby crawled at, speed is actually equal to distance divided by time. So it'd be the 9 feet divided by 20 seconds right there. And if you want to know what the magnitude and direction of the velocity, it's going to be 6.7 feet divided by 20 seconds. And then you'd also have to add to the left of its original path. Okay, so that's how we deal with velocity. Average velocity, when you look at this slope right here, and we're dealing with linear motion at this point, so we can talk about speed or velocity being the same if the direction's not changing, and if you're not slowing down and speeding up. What we have here is distance over time, which is in a linear sense, it's the same as displacement over time. Velocity is actually the slope of this graph right here. Okay, so keep in mind, whenever you're seeing a d versus t graph, the slope is going to be your velocity or your distance, or your speed, sorry. Okay, now another thing that we'll do with graphs sometimes is we will figure out instantaneous slopes and average slopes. This is an instantaneous one, okay? Notice, like, to calculate this slope right here, the slope is the speed or velocity, and I would just look at it as a slope problem, basically. Notice it's a positive slope. If I want to know what change of y over change of x is, I'm going to go final position minus original position. That's my y. This minus this, divided by a change of time, okay, 10 minus 0, come up with a positive 6 meters per second. Now, if I wanted to calculate the sections 2 and section 3, I'm just dealing with it as a slope formula. Notice how the slope for this one is 0. It's a flat slope. There is no slope. Therefore, I'm not moving at that point. My position is not changing with respect to time. My speed or velocity is 0 meters per second. And this is a negative slope here. A negative slope is going to tell me that I'm moving backwards with my speed or velocity. And you can calculate that out by going change of position, okay, change of x, okay, final minus initial, over change of y, sorry, that's the wrong, change of y, final minus position of y, over change of x, and it's all worked down here to figure out what your velocity is at this point. Okay. Another thing that we look at is instantaneous velocity. Sometimes we're going to refer to this as the derivative velocity of displacement with respect to time. Now, you can use calculus and do derivatives at this point if you have an equation for this line. But what we're going to do it as, we're just going to draw tangent slopes. So if I want to know what the car's instantaneous velocity is at 1.2 hours, what I could do is just establish where 1.2 hours is on the slope and draw a tangent slope at that point. And then I could just calculate through change of y over change of x. I could calculate my slope at that point, and I've done it right here to show you the answer of how to work that out. That's a skill you'll want to have. Another thing we can do with graphical interpretations of speed and time is we can do integrals too. And so again, if you had an equation, you could do a calculus version of an integral. But what we have here is simple shapes that we can do an area under the curve integral. Now, the way to notice this is with velocity with respect to time. If you look at the integral of that, that's basically taking your y-axis and multiplying it times your x-axis. And when I do that, it's basically saying like meters per second times second. The seconds cancel, and I'm left with meters. I've got an integral that gives me the displacement of the object that's going through the motion. And so in this case, what I could do is I could take an area, and this is like a triangle here. And with that area, I could just say, well, this is like a 1/2 base times height kind of situation. So my base is 2, my height is 2, 2 times 2 is 4, take half of that is 2. This little integral right here, this little area, is 2 meters. The buggy would have gone 2 meters of distance or 2 meters of displacement during that frame of time. Now I've got worked out on the next page to show you the whole entire result there and how I calculated all those integrals. So that's our first lesson here for linear motion, dealing with distance, displacement, speed, and velocity. And we've got some practice problems and things that'll come up to help you practice these concepts. Well, that's it today. Have a great day. Enjoy yourself.